Hello everyone, welcome to our new video. In this video, we want to continue creating the spectrum analyzer using locking amplifier technique we described in the previous video. If you didn't get a chance to watch the previous video, please before watching this video, go ahead and watch that video because I talk about how mathematically we can extract the amplitude and phase of a sine wave that we receive in our receiver. So based on what we talked in the previous video, assuming that we have a sine wave, because when you look at a signal in frequency domain, you can uh, the signal constitutes of multiple sine wave tones that are added to each other. So assuming that we want to see at a given frequency, let's say 1 gig, 2 gig, 1.3 gig, or the frequency that we want, how much is the amplitude and the phase of the signal, we can use the locking amplifier technique to extract the amplitude and phase information. And ADALM-PLUTO software-defined radio gives us the ability to do that. Um, you can see in the block diagram of the AD90-361 integrated circuit, we have after the receiver, we have an LNA, then we have a mixer which uses I and Q signal that are 90-degree apart from each other to create the down-converted I and Q baseband signal for us. And then this is passed to ADC, and we can extract information once the ADC converts this analog signal to digital for us. So now we want to see how we can implement that in Python. Uh, so just want to I have the code side by side to the block diagram. So when I'm describing, I can describe what is the block that it's getting affected by these settings. So first of all, we need to, based on the IP address of our device, we need to get connected to our SDR. And this is as simple as it gets. We just like SDR equal to AD9361, then the IP address. Then SDR as we now, if the IP address is correct, we get connected to the SDR and we can change its settings. One thing is now we want to create the locking amplifier. One thing we need to do is define the sample rate of our ADC. Define the RxLO, which is the LO that is fed to the mixer. We need to define that frequency. We need to define this that filter bandwidth. So one is SDR.sample rate. Here in this case, we just define 4 megahertz, meaning that our ADC sample rate is 4 megahertz. You can actually see what changes here when we change these settings. One is we have these oscillators that generate the oscillations we want for our TX, for our RX, and also the clocking for the ADC, right? But the but then with changing these dividers, the ratio of these dividers, we can change the clock of the ADC, right? So then when we define the SDR.sample rate, essentially we are changing the divide ratios here, right? Or we are changing when we are changing the RxLO, we are changing the frequency of this LO generation oscillator here, right? So that's one thing. The other thing is that, as you know, if I just want to show here, as you know, you can see here the ADC clocking is 25 to 640 megasample per second here, right? But then one constraint we have if we are interfacing with a USB 2 to our AD9361, which we are in this case. USB 2 maximum frequency, the maximum speed is 400 mega bit per second, right? So then uh, we might run into issue when we want to, if our ADC is faster than the clock of the ADC is faster than what we want, right? Or basically the timing between the ADC to our USB 2 connection. Uh, so what we do is that in the future videos, we try to see if we can get connected to our ADALM-PLUTO using Ethernet to bypass that um, uh, interfacing speed limitations. But for now, if you are using USB 2, it means that we need to make the output samples of the ADC to whatever speed they have compatible to our interface output we have, because uh, we even, like, let's say our USB 2 has like 400 megas bit per second. There are some overheads when we are interfacing here. There might be some frame synchronizations or other requirements that reduce the update rate we can have at this interface that goes to our USB 2 then to the computer, right? So this is why we have these RX estimations and filterings here to kind of make the output ADC speed compatible to the output of the to the USB 2 connections we have here, right? So this is one thing to note here. There we can try playing with the firmware to, instead of using 9361, I use 9364, which essentially has a uh, higher ADC update rate, or basically supports higher update rates for the DAC and the ADC. But for now, let's say we are using 9361, which only supports max to 30 mega sample per second, right? So that's the maximum sample rate we can go. Then, okay, so this is the discussion about what are these decimation filters, right? Then we are setting the sample rate, we are setting the RF bandwidth, then the buffer size, how many, because when we are reading back the ADC, we in ADALM-PLUTO essentially we have this memory that um, with the size that we define, it reads that number of points and stores them in the memory. We can set the number of samples that we want to read for each time we just say SDR.RX. For now, I just set it to 4,000 multiplied by 8. One other thing to note is here, this these gain settings, gain controls, as we talked in the previous videos, we have a VGA in our receiver that can be set either with manual gain. So when we set the gain to be 30 dB, it just sets the VGA or variable gain amplifier to 30 dB. But we can also put it inside the feedback. So when based on the amount of the power received at our receiver sets the variable gain amplifier, right? But now, because we just want to uh, without any extra processing, we just want to see how much is the difference between each frequency in terms of the received amplitude. We just set it to manual and then set it to, for this case, 30. Once our SDR is configured, we go to the next step, which is finding the spectrum of the received signal. As I mentioned in the previous video, what we do is that we sweep the LO frequency here. Then for each given LO frequency, we extract the received amplitude and phase, and then uh, just plot that. What I do here is that based on the sweep that I want, I create the array of the frequencies that I want to sweep, which is I set the start and stop frequency for it. Uh, then I linearly create the array of frequencies that I want to look at. Then each time in my sweep, uh, I just increased like once one frequency is done, I increase the sweep index. Then uh, for the new sweep index, I find what's the frequency. I set the RxLO to that new frequency, which is done by str.rx underscore LO. Then this means that I change the RxLO. Then now what happens is that uh, my LO is locked to this new frequency that I want to look at. So when I read back the ADC data, which I will done after just write just some um, str.rx to clear the buffer, I just read back the str.rx values and create the received signal and pass it to the extract amplitude phase um, function that extract the amplitude and phase. This function, which I talk about later, gives me the amplitude and phase, the extracted amplitude and phase, and I just plot it, right? So yeah, so now we want to talk about how we extract the amplitude and phase. Okay, now that we have the RX signal, which is read back from the ADC output, um, and that ADC output is essentially the uh, digitally converted signal, the down mix signal from the output of the mixer. We just need to go and extract the amplitude and phase of it. If you watch the previous video that I discussed this in detail, we know that now that we have a sine wave and we want to find its amplitude and phase, we basically, when we multiply to a sine or a cosine, uh, we can find a variable am over 2 cosine phi, or in terms of when we multiply to sine, we have a sine phi here. We basically need to, after the signal is down converted, we need to pass it through a low pass filter to get this term, to remove the higher frequency signal 2 pi ft. This is done here with these two codes. One is we want to create a low pass filter. There are multiple ways to create a low pass filter. You can even simply just average the received signal, uh, or you can go ahead and implement different types of low pass filters. The one that I use here is a very uh, simple simple version. Just want to show, so I'm using sci-fi uh, library in Python. This is a very useful library. You can create all sorts of DSP required functions with it. One thing is that it can calculate the coefficients that you need for your low pass filter for you. In this example that I'm showing from their uh, wiki page, they want to create a Kaiser filter with a known transition width for the low pass filter, and they know they want the filter to have a very specific stop band rejection. So here they normalize the width they want, which is here is 5 hertz to the Nyquist rate. Nyquist is your sample rate divided by 2. Then they define the ripple in dB. Then using this function, they find the values for beta and the or a filter order that satisfies this requirement. Then using this FIR win, And you can just find what are the coefficients for your filter, right? Uh, I just wanted to show this to use to show you how capable is this library. But instead of using this caser, I'm just designing a very simplified linear low pass filter here. FIR win, I just give the order 11 order to it. Then I just need to define what is the cutoff frequency that I want. And if I want 10 kilohertz, I need to give it the normalized cutoff frequency with respect to the Nyquist rate, which is sample rate divided by 2. So this will give me the coefficients for my filter. I define it as B. Then I just, after I have the coefficients for my FIR filter, which is only, as you know, FIR only processes our X data, and it's not dependent on our previous uh, filter output data, which are the output of the low pass filter, or Y. So basically, after I have the coefficient I using L filter, I just give the coefficient B to it, and because we are FIR, we just set the denominator here to 1 and then pass the main signal to it. So after this, because we have the low pass version of our signal, and as you know, because now we are dealing with because in Python and Pluto output, it's already in complex format. So it it has done the sine and cosine simultaneously for us, and it has given us a complex signal, right? So we just need to, after the low pass, we just need to find the amplitude of that complex signal and that the phase. Uh, and this is the phase and the amplitude of the received sine tone for this given LO frequency. So now let's go and test how well the created spectrum analyzer works. So I'm trying to create different examples to see the behavior. One is as you can see in the top screen, I have connected a second ADALM-PLUTO to my main spectrum analyzer that I generated with ADALM-PLUTO. That second ADALM-PLUTO is using the IP.2, and with that, the reason I'm doing it is to generate a, a, a signal that I can see, it's a spectrum at my receiver. So this is basically a signal generator for me. And for this, I just define the TX sample rate to be 30, and I want to create a signal with a TXLO at TXLO around 1.6 gigahertz. Uh, that's where I set my TXLO. And for this, I just set the hardware gain to be minus 30. As you can see in my setup, I have also added a attenuator between TX and RX because you want to have good control in your received signal power. If the received signal power is too much, it may damage your receiver. Um, so yeah, that's the configuration of TX, and we create a TX data and just transmit it. The TX data that we are generating is just two sine tones here. So essentially, the output would be these two sine tones, which one is zero point 0.1 megahertz, the other is 15 megahertz. When they get multiplied to our TXLO, we will have two tones. One is only zero point 0.1 megahertz below or above 1.6 gigahertz, and 15 megahertz above and below the 1.6 gigahertz. So around 1.6 gigahertz and 1985 or 1615, we should see some frequency uh, information. One other thing to just make this faster is for this, I just made the sweep start and stop around the frequency tone that we want to see. So it starts from 1.550 megahertz to 1.650 megahertz. And I'm sweeping with 500 points between these two frequencies. So let's run the code and see how it works. Okay, I have started the code. I just waiting to, because the sweep is uh, it takes sometimes, because as we increase the number of points we want to see, uh, it takes more time. But so this is how it's working. You can see our sweep has started from 1.55, and we are sweeping. I changed the sweep points to 1000 points to 1.65. So between each point, we are 100 kilohertz apart. So we were expecting to see a tone 15 megahertz apart from 1.6 in both up and down. And you can see it's right now, as the sweep is continuing, you can see it has, if I just pause the sweep for a second, you can see here we are actually at around 1.85, just in the middle here. And then we are seeing the tone at 1.6 because another tone was zero point 0.1 megahertz, right? So we are seeing those tones around here, and then the upper side, which is 1.615, right? So we are seeing this beautiful spectrum that is coming from our TX in our RX with very good uh, accuracy. So one thing to note here is that uh, you can see the tones 15 megahertz apart from the main tones. The second sine wave has the amplitude the amplitude in dB. You can say it's like 8 dB less. And one of the reasons for that is because these tones, because we will see 100 kilohertz, minus 100 kilohertz here and plus 100 kilohertz here. And there is a chance that because of the accuracy of our RxLO, they kind of are mixed together. So we are seeing the power, the equivalent power of uh, them added to just one tone here. And also, as you get apart from your, um, as you get closer to your DAC sampling rate, because for this case we set the DAC sampling rate in TX around 30 megasample per second, and our tone is 15 megahertz, right? So essentially it means that uh, and number of buffers that you read or write to create this signal, you may not give the whole picture, whole sine wave to the DAC, or the DAC may, because you are just sampling very close to the Nyquist, not be able to see all the transition behaviors. So there is some spectral leakage, which will reduce the power that we receive. That is one thing to note. The other, you can see the phase here. One thing to note here is that as we are sweeping the phase here, right now, because the frequency that we are sweeping has a tight range. It's from 1.55 to 1.65. So the frequency is not changing by that much. But one thing to note here is that with these high frequency locking amplifiers, what happens is that because your frequency is high, so your circuit sizes, your cable sizes become comparable to the wave lambda. It means that when you are changing the frequency, you are essentially changing the wave lambda, or wavelength, which will have an effect on the phase. We will see this in other examples that I try to talk about in our next videos. Because now that we have this beautiful and accurate locking amplifier, we can create many things from it. One example is that if we just connect the RX to an antenna in free space, you can see the frequency spectrum of the environment around you. You can detect the you can detect you can see actually the Wi-Fi signal or Bluetooth signal around you, or even LTE or other frequencies, which is a very cool thing. Another thing that we will create with the locking amplifier in our next videos is that we can use this method to create a circuit essentially to give us the frequency response of a circuit that we want. For instance, this attenuator that I have added here, or we can see if we add a low pass filter, what is the frequency response of that low pass filter, or other things we can create this with this locking amplifier. But now we don't want to make this video too long. But now with this ability of this locking amplifier, we can create all sorts of accurate measurements that we will discuss in the next videos. Thank you for watching. Please tune in, please subscribe. So as we go on, you get notifications for the next videos. And also please give me feedback on what you want to see, or what are the ideas you have that we can work on in the comments. Thank you.